There's a force beneath the ocean's surface that you can't see from a boat, can't feel from the shore, and until recently, we didn't even know existed. It's not a creature. It's not a current in the way we usually think of them. It's something far stranger. A swirling mass of water, sometimes the size of a city, sometimes larger than entire countries, spinning silently through the depths for months or even years at a time. Scientists call them mesoscale eddies, oceanic vortices, and they're everywhere. Right now, thousands of them are rotating through every ocean on Earth, carrying heat, nutrients, and life itself across distances that would take a human lifetime to swim. These invisible whirlpools don't just move water, they reshape climate patterns, fuel entire ecosystems, and in some cases, they're literally changing the chemistry of our planet. We're only beginning to understand how they work, and what we're finding is extraordinary. Stand on the deck of a ship in the middle of the Pacific and look out at a flat, endless horizon. You'd never know that beneath you, hundreds of meters down, a vortex the size of Manhattan is spinning counterclockwise, pulling cold water up from the abyss. The surface looks calm. The satellite images show nothing unusual. But if you could see beneath the waves, you'd witness a massive rotating cylinder of ocean, organized and persistent, drifting westward at walking speed. This is a cyclonic eddy. Water at its core is colder than the surrounding sea, denser, spinning like a slow-motion tornado lying on its side. As it rotates, it drags deep water upward, water that's been sitting in darkness for decades, loaded with nutrients that haven't seen sunlight since they sank from the surface years ago. And when that nutrient-rich water hits the sun, something remarkable happens. Plankton blooms erupt. Tiny organisms that form the base of the ocean's food chain suddenly have everything they need: light, minerals, nitrogen, phosphorus. Within days, the water turns green with life. Small fish gather, larger predators follow. The eddy becomes a traveling oasis, a moving ecosystem drifting across an otherwise barren stretch of ocean. But not all eddies behave this way. Spin one in the opposite direction and everything changes. Anti-cyclonic eddies rotate clockwise in the northern hemisphere. Instead of pulling water up, they push it down. The core is warmer, the water less dense, and instead of feeding life, these eddies can create oceanic deserts, zones where nutrients are pushed so deep that the surface becomes starved. Plankton populations crash, fish move on. The water turns a brilliant empty blue. Two eddies, identical in size, spinning in opposite directions, creating entirely different worlds. One a feast, the other a famine, and both invisible from above. Here's what makes this even stranger. These eddies don't just appear randomly, they're born from instability. When a major ocean current like the Gulf Stream flows along a boundary, friction and temperature differences create wobbles in the flow. Sometimes those wobbles break off, pinching away from the main current like a droplet separating from a stream of water. Suddenly, you have a spinning mass of ocean that's no longer connected to anything, a rogue piece of circulation drifting on its own. And once it forms, it can last for months, traveling thousands of kilometers before it finally dissipates. Scientists tracking these eddies have watched single vortices cross entire ocean basins from one continent to another, carrying water that originated in a completely different climate zone. An eddy born off the coast of Japan can end up near Hawaii, still spinning, still carrying the chemical signature of where it started. The energy contained in these eddies is staggering. Collectively, mesoscale eddies account for about 70% of the ocean's total kinetic energy. Not the massive currents we learn about in school, not the tides. These spinning vortices, most of which we can't even see, hold more motion, more raw power than almost anything else in the ocean. And that energy doesn't just sit there, it gets transferred. When two eddies collide, they can merge, combining their rotation into a single larger vortex. Or they can shear each other apart, fragmenting into smaller spirals. The ocean's surface, if you could see it in detail, would look less like a smooth conveyor belt and more like a chaotic soup of interacting whirlpools, each one pulling and pushing against the others. But the real mystery isn't how these eddies move. It's what they're doing to the planet. For decades, climate scientists focused on the big currents, the Gulf Stream, the Antarctic Circumpolar Current, the thermohaline conveyor belt that moves water from pole to pole over the course of 1,000 years. Those are the systems that textbooks highlight, the ones that transport heat on a global scale. But recent research has revealed something unexpected. Mesoscale eddies, these temporary chaotic swirls, might be just as important. They move heat laterally, from the equator toward the poles, but they do it in a way the major currents can't. Instead of following predictable paths, eddies wander, carrying pockets of warm or cold water into regions where they don't belong. A warm core eddy drifting into a cold zone can raise local temperatures by several degrees. A cold core eddy entering tropical waters can create a temporary cooling effect. And when you add up thousands of these interactions happening simultaneously across every ocean, the cumulative impact on global heat distribution becomes massive. In fact, scientists now believe that eddies are a dominant driver of marine heat waves. These are prolonged events where ocean temperatures spike far above normal, sometimes for weeks or months, devastating ecosystems and altering weather patterns. For years, researchers assumed these heat waves were driven primarily by atmospheric conditions, unusual wind patterns, or high-pressure systems sitting over the ocean. But detailed modeling has shown that in many regions, it's the eddies doing most of the work. A warm anti-cyclonic eddy parking itself in one spot can trap heat at the surface, preventing it from mixing downward. Temperatures climb, marine life that can't tolerate the heat begins to die. Coral reefs bleach, fish migrate away, and when the eddy finally moves on, it leaves behind an ecosystem struggling to recover. The Southern Ocean is particularly vulnerable to this. It's one of the most turbulent regions on the planet, home to the Antarctic Circumpolar Current, the only current that flows all the way around the globe without hitting land. That current generates massive eddies, some of the largest and most energetic in the world. And over the past few decades, scientists have noticed something alarming. The eddies in the Southern Ocean are getting warmer. Not the surface water, the eddies themselves. Measurements taken from thousands of underwater sensors show that temperature anomalies inside these vortices have been increasing, especially in the subsurface layers where the ocean stores most of its heat. Nearly half of all extreme temperature events recorded in the Southern Ocean occur inside eddies. And as the planet continues to warm, these eddies are expected to intensify, transporting even more heat into regions that are already experiencing rapid change. But eddies don't just move heat, they also move life. Marine larvae, the tiny offspring of fish, corals, crabs, and countless other species, drift with ocean currents during their early development. For decades, scientists assumed this dispersal was passive, that larvae simply went wherever the water took them. But tracking studies have revealed that eddies play a far more active role. A cyclonic eddy with its nutrient-rich core can become a nursery, providing food and shelter for larvae that would otherwise starve in the open ocean. As the eddy drifts, it carries those larvae hundreds of kilometers from where they were born, delivering them to distant reefs and coastlines. This long-distance transport connects populations that would otherwise be isolated, maintaining genetic diversity and allowing species to colonize new habitats. Without eddies, many marine ecosystems would be fragmented, cut off from the genetic exchange that keeps them resilient. And then there's the carbon. One of the ocean's most important jobs is absorbing carbon dioxide from the atmosphere, pulling it down into the deep where it can be stored for centuries. This process, called the biological carbon pump, relies on plankton. Microscopic organisms at the surface absorb CO2 through photosynthesis, then die and sink, carrying that carbon with them into the depths. But this system is far more complicated than it seems, because not all regions of the ocean are equally productive. Some areas are nutrient-rich and teeming with plankton. Others are essentially deserts. Eddies blur those boundaries. A cyclonic eddy moving through a low productivity zone can temporarily fertilize it, sparking a plankton bloom that wouldn't have existed otherwise. That bloom absorbs carbon, and when those plankton die, they sink, taking carbon with them. Recent estimates suggest that eddies may be responsible for transporting millions of tons of carbon into the deep ocean every year. Carbon that would have stayed in the atmosphere if not for these swirling masses of water. The ocean's ability to mitigate climate change doesn't just depend on the big currents. It depends on thousands of invisible vortices doing work we're only beginning to measure. But not all eddies are natural. Some of the largest, most persistent swirling systems in the ocean are driven by wind and Earth's rotation. These are called gyres, and they operate on a scale that makes individual eddies look tiny by comparison. There are 5 major gyres, one in the North Pacific, one in the South Pacific, one in the North Atlantic, one in the South Atlantic, and one in the Indian Ocean. Each one is formed by a ring of currents flowing in a massive loop, driven by prevailing winds and the Coriolis effect, the force created by the planet's rotation. And at the center of each gyre sits a zone of relative calm, a region where water circulates slowly, almost stagnant compared to the outer currents. These calm centers are the ocean's dead zones, places where debris accumulates, where plastic floats for years, and where the natural rhythms of ocean circulation break down. The most famous of these is the North Pacific Gyre, home to what people call the Great Pacific Garbage Patch. The name is misleading. It's not a solid island of trash. It's a diffuse zone, roughly twice the size of Texas, where plastic debris has collected in concentrations far higher than anywhere else in the ocean. Most of it is microplastics, fragments smaller than a grain of rice, suspended in the water column like a toxic soup. Fishing nets make up nearly half the mass, ghost gear lost or discarded by commercial fleets, tangling into massive drifting webs that trap marine life for decades. The gyre doesn't create the plastic, humans do. But the gyre's circular motion draws it in, trapping it, concentrating it, turning a global pollution problem into a localized catastrophe. And it's not just the Pacific. Every major gyre has its own garbage patch, though the others receive far less attention. The North Atlantic, the South Pacific, the Indian Ocean. All of them are accumulating plastic at accelerating rates. What's truly disturbing is that these garbage patches are no longer just trash. They're becoming habitats. Species that normally live on coastlines, barnacles, crabs, anemones, have been found living on plastic debris in the middle of the open ocean, thousands of kilometers from the nearest shore. They're surviving, reproducing, forming communities on floating trash. Scientists call it a neopelagic ecosystem, a new kind of ocean life that shouldn't exist but does. Coastal organisms that evolved to cling to rocks and driftwood are now clinging to detergent bottles and fishing buoys, drifting with the gyre's rotation, potentially spreading invasive species to regions they've never reached before. The ocean is adapting to our pollution, and we don't yet understand what that means. But the largest vortex in the ocean isn't a gyre. It's not even a single eddy. It's a circulation system so vast, so fundamental to the planet's climate, that if it were to fail, the consequences would be catastrophic. It's called the Atlantic Meridional Overturning Circulation, or AMOC, and it's the ocean's conveyor belt. Warm surface water flows north from the tropics, carried by the Gulf Stream and the North Atlantic Current. As it reaches the cold waters near Greenland and Iceland, it loses heat to the atmosphere, becoming colder and saltier. Cold, salty water is dense. It sinks, plunging thousands of meters down to the ocean floor, then flows south along the bottom of the Atlantic, eventually spreading into the Indian and Pacific Oceans. This creates a loop, a continuous cycle of sinking and rising that takes roughly 1,000 years to complete. 1 cubic meter of water sinking near Greenland today won't return to the surface until the year 3025. This circulation transports an unimaginable amount of heat, about 1 petawatt, roughly 50 times all the energy humanity uses in a year. That heat is what keeps Europe habitable. Without the AMOC, cities like London and Paris would have climates closer to those in Canada. The current keeps the North Atlantic warm, moderates temperatures across an entire continent, and drives weather patterns from the Arctic to the equator. But the AMOC is slowing down. Measurements over the past few decades show a consistent weakening, likely driven by 2 factors. First, the ocean is warming. Warmer water is less dense, which makes it harder to sink. Second, Greenland's ice sheet is melting, pouring massive amounts of fresh water into the North Atlantic. Fresh water is less dense than salt water. It stays on the surface, preventing the cold, salty water beneath from sinking as deeply as it should. If enough fresh water enters the system, the entire circulation could stall. Scientists have been debating for years whether the AMOC is approaching a tipping point, a threshold beyond which it could collapse entirely. Some models suggest it's unlikely to happen this century. Others warn that early warning signals are already appearing, subtle changes in temperature and salinity patterns that indicate the system is losing stability. If the AMOC were to shut down, the effects would be immediate and severe. Europe would cool by several degrees within a decade. The tropical rain belt would shift south, altering monsoon patterns across Africa and Asia. Sea levels along the east coast of North America would rise faster than anywhere else on the planet because the AMOC circulation currently pulls water away from the coast. Without it, that water would pile up, and the ocean's ability to absorb carbon would weaken, accelerating atmospheric warming even further. The AMOC is not a distant abstraction. It's a living system, constantly adjusting to the planet's changing conditions. And right now, it's under stress. We're watching it in real time, tracking its strength through a network of sensors stretched across the Atlantic, measuring temperature, salinity, and current speed at dozens of locations. The data shows variability, short-term fluctuations that make it difficult to predict exactly what will happen. But the long-term trend is clear. The circulation is weakening. How much weaker it will get, and whether it will reach a point of no return, depends on decisions we make in the coming decades. So, what are we looking at here? Thousands of invisible eddies, each one a self-contained world, drifting through the ocean, transporting heat and nutrients and life across distances most people will never travel. Massive gyres collecting our plastic waste into slow-motion whirlpools that are becoming ecosystems in their own right, and a planetary-scale circulation system that's been running for millions of years, now showing signs of instability. These aren't separate phenomena. They're all part of the same system, different expressions of the ocean's constant motion. And that motion is what makes Earth habitable. It redistributes heat from the equator to the poles. It cycles nutrients from the deep to the surface. It absorbs carbon, moderates climate, and sustains ecosystems from coral reefs to polar ice. The ocean doesn't just sit there, it moves. And the way it moves, the patterns of circulation we're only beginning to map, determines everything. The challenge now is learning to see what's invisible. We've built satellites that can measure sea surface height with millimeter precision, detecting the subtle bulges and depressions created by eddies. We've deployed thousands of autonomous floats that drift with the currents, measuring temperature and salinity as they go. We've developed computer models that can simulate the ocean's behavior with increasing accuracy, predicting where eddies will form, how they'll interact, and what impact they'll have on climate. But the ocean is vast, the interactions are complex, and every new dataset reveals patterns we didn't expect. We're still learning, still discovering, still trying to understand how a planet-sized system of swirling water manages to keep itself organized despite the chaos. And that's what makes the oceanic vortex so extraordinary. It's not one thing, it's a principle. Anywhere water moves, vortices form. Anywhere currents interact, eddies spin off. The ocean is never still. It's always rotating, always mixing, always transporting. And those invisible swirls, those spinning masses of water we can't see from the surface, are doing more work than we ever imagined. They're feeding ecosystems. They're moving heat. They're storing carbon. They're connecting distant parts of the planet in ways that defy simple explanation. The oceanic vortex isn't just changing things. It's the reason the ocean works at all. Thank you for watching this video. If you enjoyed it, please like, share, and comment down below, as it helps let others know they should watch this video. Also, consider subscribing and hitting the bell to get notified of our newest videos. See you next time.